Still remember the problem or you forgot? Let me reiterate. So here we have an organization that has only one physical network but with 4,000 hosts. Subnetting doesn't help, so we have to give this a class B address that leads to very poor efficiency. Now, how do we solve this particular problem? How about assigning multiple class C addresses? So that way you can maintain high efficiency. So how many class C addresses do you need to allocate for this? 16, right? Where each class C address caters to 2 to the power of 8 hosts, roughly. Is there any problem with this approach or are we done? Well, we are never done. So the problem with this is now for one organization, you have 16 entries in the routing table. So this is again going to lead to scalability issues where you are representing one organization by 16 entries. This will not do. So what can we do? Can you think of a solution? You should be able to think. It may be a bit tricky, but we have seen similar principles in practice before. Simple solution: assign multiple contiguous class C addresses and then you aggregate. What do I mean by this? So for this specific case, you take this address range. So this class C addresses that are in this range where the top 20 bits in this range are the same. This corresponds to 0001. And then designate a 20-bit network number. So what would you advertised as the organization's network number? Right? 222.7.16/20. So this is what you would advertise. So a router somewhere in the internet will know that to reach this organization, it will just maintain one single entry. So this solution goes by the name supernetting. Earlier was subnetting, this is supernetting. So this is a quick summary of what we have seen. In subnetting, one class address is shared among many physical networks. In supernetting, multiple class addresses are shared among one physical network. In supernetting, this physical network I also at times will refer to as autonomous system. Basically, an organization managing a particular network, we refer to it as an autonomous system. So the conclusion across both of this is that the network portion can take on any length. What all lengths do you think the network portion can take, given that we do subnetting as well as supernetting? Well, it can take on any value between 2 to 32. 2 because the class A, the first bit is always fixed at 0. 32, just like a one-man army, you can have a one-host network, in which case you have to, the network mask will have to specify all the 32 bits. So this leads to what is called a classless inter-domain routing. So there are no more classes A, B, C, D, E, because the network portion can be of any length. So we use a new notion to represent network numbers. This is called IP prefixes. So the address block is represented in this particular fashion, where A is the address prefix and X is the prefix length. And this X, as I mentioned, can take on values from 2 till 32. X is also represented as a network mask, where that /21, for example, is represented like this. To concretize, this 222.7.16-20, where the mask corresponds to this, represents addresses in the range from all the way here to here. So a router that maintains this entry will match the destination address in an IP packet. If it falls anywhere within this range, it is going to forward it on the interface that is specified by this particular entry. A reiteration of what I said. So routers are now going to do a prefix match. Basically, they will ask this question: does the destination address fall in the range of addresses captured by the prefix? If so, send it out on the interface specified by this particular prefix. So this works great if the internet topology is a tree where the shortest path between networks is unique. But unfortunately, the internet topology is a graph, mainly because many networks at times are multi-homed for fault tolerance or load balancing purposes. Again, let me explain what I mean by multi-homing. In the previous example, the 190.23.8.0/21 network was connected to the internet via R2, which is going via R1. Now it's possible that I could also directly connect it to the internet via some other router R6. So this network is now multi-homed. Now it can access the internet both via R1 as well as R6. As mentioned, you do this mostly for fault tolerance and redundancy purposes. Now if you did something like this, now you will have two matching prefixes as part of a router's forwarding table somewhere in the internet core. One corresponding to this and another corresponding to this. This is what maybe R2 will advertise and this is what R6 will advertise. Now this address belonging to this particular network is going to match both these prefixes. Now who do you send this packet to? Simple rule, go with the longest prefix match. So that's what you implement. Now if you look at the task of forwarding, now we have to do the longest match between a destination IP address and a variable length prefix as part of the forwarding table. And when we covered the router design, you want to do it extremely fast. So there's a lot of research that happens in this space. We are not going to cover all that. Now are we done with addressing? Not quite. We are done as far as this video is concerned. There are more issues we will cover as part of other videos. So here is a summary of what we have seen so far. We found that the class-based addressing is not scalable. So to address the scalability issues, we looked at two solutions. One is subnetting, where we share a single class address among multiple physical networks. Another is supernetting, where we share multiple class addresses on a single network. So this has led to what is called a classless addressing scheme, where we employ the longest prefix match as part of router, and this is what is widely used now. So we will see other issues with addressing and solutions for the same in other videos.